Vikram Kapila is a full professor at New York University. I think we have been working together for like a couple months and working together on an NSF proposal. So I think he has been always very creative and also visionary, not only conducting high caliber research, but also promoting mechatronics education in the broader like population. I think Professor Kapila, the stage is yours. Thank you. We cannot hear you. Could you unmute yourself?
Can you hear me now?
Yes. Yeah.
Good. And you can see my slides, right?
Yeah.
Okay. Let me first begin by thanking the workshop organizers for inviting me. Although I am not doing research per se in soft robotics, I hope that with this talk you will get some ideas on how you might be able to integrate your research also in education. So the title of my presentation is Research and Education at the Convergence of Frontier Technology, and I'm at the NYU Tandon School of Engineering. Let's go to the next slide. So very quickly, let me start with the outline of this talk. I'm going to give you an overview of our approach to experiential learning in mechatronics and robotics. And I'll discuss how such an approach may be able to make a positive contribution to the workforce of the future. I will also describe my research that I've done over the last decade in my lab in the area of mechatronics and robotics, with particular focus on the design and development of highly natural and intuitive human-robot interaction with the use of mobile devices such as smartphones and tablets, and some of their applications in the healthcare area. And then I'll transition to our more recent work that has been geared towards convergence research, and I'll show you some of this transition. So in the 21st century, we are witnessing an economy that is characterized by and driven by the innovation, and it has led to a startup culture that requires that engineers and technologists, as well as product developers, work and learn from team members that come with varied backgrounds and experiences. The ability of these team members to function and thrive in such an environment must be inculcated during their formative years in the undergraduate and graduate education through a highly interdisciplinary framework that includes also a lot of the experiential learning. The classroom and lab education should also be connected with an entrepreneurial experiences so that the students have broad career opportunities. The trends that we witnessed in the last few years indicate that there is a need for engineers who have a broader education and experience so that they can serve as journalists instead of being niche specialists. Engineering graduates need to be able to function in small teams that could be rapidly reconfiguring in response to emergent need. So the era of lone warrior is not there anymore. So in response, so why is then mechatronics and robotics useful field to work in? Essentially, mechatronics and robotics provide an ideal technology platform on which the graduates of these disciplines can develop new businesses and venture that add societal value. Mechatronics and robotics disciplines can also spark intellectual curiosity of students and engage their interest in experiential learning and creative exploration. It allows students as well as the curricular developers opportunities to have a highly modern curriculum that is more relevant to the interest of students. It can address the demand for workforce that produces graduates with broad interdisciplinary education and practical experiences. And then obviously there are numerous emerging trends, maker spaces that are becoming commonplace in all kinds of businesses that see the potential for mechatronics and robotics. So in response, within the last 4 years, starting in about 2016, we have created a new master's in mechatronics and robotics that has 4 foundational courses in mechatronics, robotics, and software tools. It also includes a course in entrepreneurship. And then additionally, students can specialize either in robot mobility or in medical robotics. We have not yet done the micro robotic option, although that is in the curriculum. And then there is a thriving ecosystem that we have built to support projects and theses for students. And hot off the press is our brand new undergraduate interdisciplinary minor in robotics that our 4 recent robotics hires have created that is going to be offered starting in fall of 2020. So we have a very thriving project ecosystem where companies can come in, partner with us through the Friends of NYU Mechatronics and Robotics program to shape the curriculum, provide internships and jobs for these graduates. So now let me discuss a little bit about our work on natural and intuitive human-robot interaction with mobile devices. There are 2 main methods that we utilize to create these HRI techniques. In one approach, the smartphone could be mounted on the test bed, whereas in the second approach, the smartphone or the tablet could be held in the user's hand. To render these novel human-robot interaction solutions, we adopt research results from varied domains, including user interaction research, machine vision research, from 3D graphics, as well as estimation and control to develop solutions for a variety of problems. So we have applied these techniques to develop highly interactive lab explorations for automatic control and mechatronics. And some of these setups could be controlled locally with students present in the lab, creating a highly enriching learning environment. But in others, the test beds could be accessed remotely, and we have published extensively in this area. Let me show you just one example of this approach where a smartphone is embedded. Let me play the video here. So the smartphone is embedded here on the inverted pendulum test bed. All of the sensors on the pendulum test bed are not being used. Instead, we are simply using visual servoing using the smartphone and implementing the control algorithm directly on the smartphone to be able to control the inverted pendulum vertically upright. So now let me transition to our more recent work that is looking at convergence research. So I'm going to discuss some of this work that we have done over the last 4 years. It's mostly driven by the realization that our world is witnessing several frontier technologies that are evolving at a rapid pace. There are several novel drivers in the current tech ecosystem that render these frontier technologies to the level of being considered as disruptive technology. So finally, I'll also look at some of the ongoing research at the convergence of frontier technology in my lab. So industries that are having difficulties filling jobs with human workers are increasingly deploying robotics to stay competitive. Robotics is one such company. I read about them only about 2 years ago in a Washington Post article. And a few months later, one of my students was hired by them. And essentially, it's a robot staffing company that you can call in to deploy robots for an industrial problem without having to pay for the robot. But robot is essentially being paid for on an hourly basis. Similarly, artificial intelligence is being deployed extensively now for applications such as policing, mortgage application processing, social media campaign, and autonomous driving. And AI and computer vision are becoming extremely common in a wide variety of applications. Augmented and virtual reality can shape people's experiences in online shopping, entertainment, as well as real estate buying. Virtual App is one of the local startups in downtown Brooklyn who are marketing high-end residential and commercial real estate using robotics and virtual reality. And I've had some students who have worked with the Virtual App. Blockchain technology similarly has pretty broad applications beyond serving as a distributed, decentralized, secure contract for cryptocurrency. And we have been using this in recent years for swarm robotic applications in our lab. So the drivers for the disruptive technology emerge from the fact that there have been advances in tech frontiers in recent years that have allowed a number of these hardware and software technologies to be democratized so that access to hardware, software, as well as knowledge has become very commonplace. What used to require maybe 20 years ago tens or hundreds of thousands of dollars to do new development in the robotics field now could be done in one's garage with basically hardware and software all acquired off the shelf for hundreds or perhaps low thousands of dollars. And then there has been an evolving culture of making, inventing, and startup that is adding more fuel to propel this disruption rapidly. So now let me look at a couple of these examples from my lab, specifically robotics, AI, augmented and virtual reality, and blockchain. Many of these technologies are converging together, and their greatest applications are going to come from interactions amongst them instead of in their silos. So in our lab, we are exploring some of these technologies and how their integration can be beneficial. For example, how you might be able to integrate AR and VR with robotics, and how you might be able to use blockchain in swarm robotics to do secure messaging and communication across multiple entities. So in the interest of time, I'm going to focus primarily on augmented reality for human-robot interaction, where our goal is to create a highly effective intermediary between robots and humans so that they can exchange the information and allow novice users to interact with robots in a shared space without requiring any specialized training. Specifically, in one such scenario, humans can inform robots in a natural and intuitive manner that can result in the desired motion of the robot and allow its end effector to reach a desired target. Moreover, the robot is going to be able to convey requisite information to the user, for example, the workspace boundary in which the robot can operate. So quickly, the motivation for augmented reality with human-robot interaction. With augmented reality, we can have a unique opportunity to render highly intuitive and enhanced human-robot interaction. It can be used to create user-friendly, generic user interfaces that can be deployed on everyday smartphones and tablets. without requiring any specialized devices for human-robot interaction. Such a system could also be used and operate with minimum alteration to the environment where the robot needs to function, meaning you don't need to put in additional sensors or overhead cameras or create special calibration routines for the robot to operate with the human user. So in this first setup, the video that I'm going to play, you are going to see a robot manipulator that is going to be controlled through a tablet-based interface. The user is holding this tablet with a user interface already loaded on it, and then the objects and the environment have a number of fiducial markers that are installed on them. The human user is able to move around freely in the environment and interact with the environment and the user through the UI to command the robot to pick and place various objects. The tablet camera is being used to sense the environment. Fiducial markers are the ones that are being used to locate the objects, and then there are homography algorithms running in the background to allow the robot and the objects to be located in the environment. This is about 4-year-old work, and you will see the progression of this work as to how we will be able to remove a lot of these fiducial markers from the environment and still be able to interact with the robot and the environment. So in this next piece of work, we are moving away from one manipulator robot and instead working with a number of mobile robots in the environment that can all be interacted with and commanded through the tablet. Once again, you will see in the video that we are using fiducial markers that are placed on the robots as well as on the objects. But now, at any given instance, only one fiducial marker affixed object has to be stationary, and that object can change from moment to moment, and that is where momentarily we affix a coordinate frame. A lot of the other information for the homography comes from measuring the sensor information from the tablet itself, the IMU of the tablet, and multiple robots could be interacting with the objects through that single tablet. You don't need to put any cameras in the environment. You don't need to put any sensors. The environment is not prepped up. So now all these robots and objects have been brought outdoors. And just with the tablet, you're able to locate, visualize, and interact with these objects. But once again, like the previous video you saw, all the objects and the robots here do have to have the fiducial marker. So now let's start relaxing some of these assumptions that we had previously. So now in this new framework, what we are going to do is marry the marker-based technique that you saw previously, but instead of having numerous markers on the environment, objects, or the robot, in this new scenario, there would be a single fiducial marker that will be placed in the vicinity of the robot to localize that robot. And then beyond that, we will be using markerless approaches that will allow us to determine patterns that belong to individual surfaces so that we are able to locate the surface of operation where the robot is going to be picking and placing the objects. And then using ray casting methods, the objects are going to be located through the user interaction on the screen, both for pickup and placement. So essentially, the human user is going to be holding a smartphone through which he or she is going to locate first the fiducial marker where the coordinate frame is going to be located, as the user is moving around using the IMU on the tablet, the coordinate frame for the original origin affixed to the fiducial marker is going to be recalled, and then user is going to drop anchors based on where the interaction needs to be done, as you will see in this video. So the user first places the origin on the fiducial marker. Then they are putting these anchors at the objects that need to be picked up and placed at various locations. The sizes of the objects are not known. The manipulator robot opens up completely, picks up the object and places it at another location. So a lot of things still that need to be done. So now we move on to the next setup, where we are extending the previous user interaction, where through an interactive approach using augmented reality objects, the user is going to be able to tell the robot where it needs to pick and place an object from, an object that is not previously seen. And through this virtual interaction, the user is also going to be able to communicate the size of the object to the robot, as well as the pose in which the object needs to be grasped and placed. So all of this is going to be done through the virtual interaction, as you will see. So the user is putting in a virtual object that is telling how tall the object is. The user is going to be able to tell the pose in which the object needs to be grasped, as you will see momentarily. So now you are rotating that AR element to tell in what orientation to pick and place the object, so on and so forth. So now we show that we can get the object size, we can get the pose, we can get the height, so on and so forth. And we do a lot of user studies with these applications. So next we move on to just doing pick and place operations to a scenario where a user needs to teach a robot to follow a certain path. For example, for machining or welding or spray painting, something like this might be useful in a flexible manufacturing operation, so that you don't need to have the robot available for teaching it what to do, and then the approach is highly user-friendly, where the operator does not need to have prior training in terms of how to work with that robot. So very quickly, first you will select some marker location. Let's say the marker is placed right by the robot, so we're going to select it as 00. We select the type of the manipulator, whether it is holding a pen or a gripper. We set the origin. We drop a bunch of virtual points that we want the robot to traverse through. We will select a particular type of manipulator. We will select the pose of the manipulator, as you will see momentarily. And then we will run the entire operation first virtually in this AR environment to ensure that the robot follows in the AR environment all of the instructions. And then by click of one button, the entire operation could be transferred to a real robot. Then we also do a MATLAB simulation to check the accuracy. And then eventually you can download the entire operation to a real robot, as you will see now momentarily. Once again, we do extensive user testing, including the NASA task load index, to figure out whether users find these approaches to be mentally or cognitively or physically burdensome. So now you can see that in one click, the real robot is able to perform the task that was taught offline. So now we move on next to teach in a similar manner the approach where you can develop an augmented reality spatial referencing system, allowing a non-expert user to tag specific locations in a physical environment, and then a real robot could be commanded to go to those locations. And then we have integrated Alexa so that the user can command by word or spoken commands to send the robot to those locations. In the interest of time, I'm going to skip this video and move on to show some other examples where we are now moving on to applying some of this to healthcare. So here we are using a Myo armband to measure Myo signals to detect human hand gestures by implementing some Gaussian filtering as well as machine learning algorithms, testing a variety of different algorithms to find out which one of them is most efficient, so that you can measure in real time human gesture and command prosthetic robot mimic those same gestures. Next, we have developed using off-the-shelf electronics and microcontrollers, mirror therapy devices for stroke rehabilitation for grasping, and then integrating that with gaming-based interfaces so that users can utilize these devices at their home to be able to do local rehabilitation in their own environment. Extending that work to doing measurement and allowing patients to do rehabilitation for their arm motion, for the range of motion. We have developed these wearable inertial sensors that a user can don on their arms as well as on the back to do the measurement of range of motion using quaternion-based measurements to avoid any singularities, but then converting these measurements to a framework where the physicians and therapists are able to understand these measurements using what is known as a joint coordinate system. And we have done the comparison of these measurements using goniometers, done the conversion to joint coordinate based measurement, as well as the comparisons using the Kinect sensors to validate that in fact these sensors will provide you the desired measurement. And then using a wearable fabric-based conductive sensor, we have created a very low-cost measurement device that can be used by therapists who are trying to do monitoring for lymphedema therapy, so that the patients are able to do their therapy remotely at home twice a day without having to come to the clinic. And we have integrated that and shown that it indeed works if you do the measurement via Kinect versus using our wearable sensor. And we have integrated that along with a microphone so that you can do the synchronization of the therapy, not only for the range of motion measurement, but also breathing, inhalation and exhalation, and how this could all be integrated for remote monitoring of patients. We bring much of this work not only to our own students at the undergraduate and graduate level, but we do a lot of integration at the K through 12 STEM education, whether it is bringing these technologies into the classroom, working with teachers so that they can bring this into the classroom, bringing in industry sponsors to come and conduct workshops for New York City teachers and educators, having teachers learn and develop lessons that align with the national standards, having the implementation in the classroom, and having sometimes teachers and students collaborate together. Beyond that, we have also done workshops for local industry in terms of how they can bring robotics to their own workplaces. because the future of work is increasingly going to be governed by integration of these smart devices and tools into the workforce. I finally want to thank our sponsors, students, postdocs, and collaborators who have contributed much to our education and research effort. And with that, I'll stop and take any questions.
Hi, Dr. Kapila, very inspiring talk. I think there's one question from the audience. He asked about, do you have some ideas how to integrate soft robots with education, either through online education or like in-person education?
So much of the work that we have done in the area of mechatronics and robotics is mostly on campus, in person, because of the need for the hardware integration and the need to have access to maker spaces. But I see very easily how soft robotics could be integrated on campus-based education. I teach a graduate course in robots for disability, and oftentimes students do projects that involve the use of soft robots, whether it is soft actuators or wearable conductive material. I have students who are developing solutions for sensory trick for dystonia. Or inflatable robots that can be used for stroke rehabilitation. These kind of things are very engaging and meaningful for students because they find that it is directly relevant to societal broader impact.
Yeah. Thank you for the like exciting talk. Yeah. Thank you again. Yeah.
Thank you again to the organizers. Let me stop my screen sharing.
Yes, please. Yeah. Our next speaker is Professor Josh Bangar.